Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
This is the podcast where we explore theories of how the world works without necessarily committing to any of them. We give theorists the opportunity to explain their ideas, and we try to make sense of them and see if we can connect them to other ideas that we've discussed on this show and in our lives in general. And today we are exploring a frontier in human knowledge, which is the quantum mechanical universe. And quantum mechanics is one of those subjects that pops up on this show all the time, everywhere from consciousness researchers to biologists, and of course physicists, the astronomers, and the whole world of physical reality seems to terminate in mathematics that many people suggest points to an unreality of the universe. And we have an incredible author with us today. This is Adam Kay, who has written a book called Escape from Shadow Physics, which explores the path that humanity has taken from studying atoms to eventually conceding that atoms are intangible mathematical pieces of reality that have no physical basis, which seems to be more or less the standard mainstream explanation for quantum mechanics, that all of reality is deeply impossible and improbable. The particles are waves and they're corpuscles at the same time. There's unrealities that emerge at every level. And of course, this eventually enables everything from black holes to analytic idealism. We've pushed back on this for years, and it's really a pleasure to sit down with somebody who's traced out the historical narrative of how this happened. And so we're going deep into the past to unravel the story. How did we end up in a situation where modern physics tells us that physical reality is made out of probabilistic equations that don't actually point to physical events at any level? That's really strange. What happened?
A lot of the conversation is centered on something that is called the hydrodynamic quantum analog, which is basically a system of classically behaving oil droplets that recapitulates a lot of the mathematics of quantum physics. And so the fundamental principle is that, well, if there's a classical system that recapitulates the mathematical shapes of quantum physics, then perhaps there's something that is capitulating the equations of quantum physics. Perhaps there is a reality, and perhaps it is worth actually studying that to understand how the universe works, as opposed to taking this approach of, well, we can't know, so why try?
Usually, I'm a little skeptical of bringing analogies into physical theory, but in this case, I think it does exactly what Anastasia said. It shows that it's possible to use the same maths to explain a truly classical physical system. No one here is saying that the quantum reality is a hydrodynamic system. We're just saying that it is an example of how those maths can be used to describe a truly classical system. Therefore, we shouldn't just throw our hands up and say, we're never going to figure it out for quantum mechanics. It's a great mystery, and it's one that needs a lot of attention, and it's one that we've dedicated a lot of effort to on our own. And in fact, we are very, very close to putting our first book out about any day now. Hopefully, we'll have that ready by the conference.
Speaking of the conference, if you like what we do on the podcast, which is that we explore the theories that we think are going to change the world, you should consider coming to Portugal to join us for our second conference called Beyond the Big Bang, where we're going to do what we do for basically everything for astrophysics and specifically the Big Bang. We're getting together a group of critics who believe that there is no good science to support the Big Bang, with theorists that are hard at work at repairing the paradigms of the Big Bang, and we are going to put them in a room at the seaside in Portugal, and we're going to spend a weekend debating, discussing, and sharing our perspectives on what the future of cosmology might look like. If you have the chance to come, you should absolutely join us in Portugal, because not only is it going to be a seminal scientific event, it is also the 5-year anniversary of DemystifySci. We started this as hairy alien puppet apes in June of 2020. We have grown significantly. We have shed our alien skins. Now you see our faces front and center. And we could not have done it without all of you who are listening right now. And so if you can come out to Portugal to have this experience with us, it would be really fantastic to meet everybody and to be able to share in what a cool community we've built over the course of the last 5 years. One of the things that we've done in anticipation of this conference is we've opened a Patreon tier, where if you purchase a year membership at the stakeholder member, you get access to the conference with that. So that includes 4 nights of lodging in Sesimbra, that includes breakfast and dinner, coffee breaks and treats during the day, access to all the talks, discussions, poster sessions. And so if you want to come, check out the link for tickets down below, where you can come to Patreon and subscribe at the annual stakeholder level, and then we'll see you there.
Speaking of Patreon, we couldn't keep doing this project without the generous support of our patrons. And I want to remind you that you can give as little as 75 cents a week, and it will actually contribute to meaningful results. That's the lowest tier on our Patreon. It's $3 a month. If you can just scrape off that tiny piece of your paycheck, it really does add up. All of you add up together to making sure that we have the time and focus to dedicate towards making this project better and better, so you have a better experience ultimately as a listener. So if it's something that you love, consider scraping off 75 cents a week and powering this project into the future.
Absolutely. And in the meantime, enjoy our conversation with Adam K., and we'll see you next time.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
It's funny because people solicit us to do this podcast all the time, and they'll send us their theories of everything. And I don't know if I was like kind of harsh with you at first, but I get so many of those that I just don't really expect much out of them anymore. And
Right.
so when I finally looked into this, and I think I just read like the first chapter or something of your book, and I was just like, this is fucking awesome. I mean, it's so similar to this project that Nasi and I have been chasing for so long. We're actually in the finishing stages of our own book, which is in some sense a parallel experience to yours, but just the history of quantum mechanics, the history of atomics can be told through so many different stories.
Mhm.
And I found, and it's what's beautiful about it from where I'm sitting is that you told a very different set of stories than the ones that Nasti and I picked when we were writing our book, but they were complementary in such a amazing and fascinating way. And I love all the quotes that you bring in. And I mean, man, when did you start this project of trying to understand what happened to physics?
So I started the book officially around the time of the pandemic, but I had opinions, like pretty strong opinions, and I had been reading around this area for a lot longer than that, like at least 5 or 6 years before that. So I think I procrastinated a whole year. I had 2 years to write the book, and then I had 1 year, and then that was basically over. And there was then some negotiations with the publisher about getting extensions, and then even that got extended. So it took a long time.
But like, what was I'm trying to like understand, obviously you don't just wake up one morning and write a book. Like the book is usually the final point where you're at this breaking point where you have some revelation about something in the universe, even if it's a fiction or something. But like just writing a book seems like the culmination of some journey that you must have started one day.
Yeah.
So I guess the question is, like, when did you start trying to figure out what had gone wrong with quantum mechanics?
So I don't think it was exactly like that. I didn't start trying to figure out what went wrong with quantum mechanics. I think what happened is that I started with a set of intuitions, which and interests. And as I pursued the interests, the intuitions just kind of got stronger. There was nothing there to like refute them or to make them weaker or to make me doubt them. And then at some point, really where I think the book took its form is I had to make the intuitions flesh, and I had to justify them in a way that would be respectable and would allow someone who didn't necessarily share them to maybe be convinced, right? Like walk them through the process. And then that, I think, was a very arduous process on my end, which started with the question like, what am I going to say? Like, how am I going to tell this story? Like, what is it that actually happened. So I kind of like had to figure it out myself, right? And I think that process is probably universal to all books. Like even if you know what you're going to say, you don't know how you're going to get there. Yeah. So
So what were your intuitions?
um, so let's see. The basic way of talking about this, I guess, would be to, I mean, this is actually a really weird story. So I'm just going to tell you guys. So, all right. So I've been reading this book called Greatness Cannot Be Planned. The main thesis of this book is that small incremental improvements you can basically plan for and then work hard and achieve them. But really big step functions in like invention or discovery can never be planned that way. Like they're not just some linear thing where you can create an optimization function and then minimize that until you get there. And it's just full of examples. And one of the examples is like an airplane, right? Like nobody set out to make an airplane. When they did set out to try to fly, they had all the wrong ideas, right? But the thing that you needed before an airplane was an engine, right? And similarly for a computer, nobody set out to make a computer. When they did, they kind of made a calculator, right? But the thing you needed for a computer was a vacuum tube. So the step right before the great discovery never has anything to do with the great discovery. It's like you can never plan how to get there, right? And that it's just a really interesting idea.
Who's the author, by the way?
I have to find it. I've forgotten. The title is Greatness. Why? Like I think it's Why Greatness Cannot Be Planned. Yeah.
Okay, cool. We'll check it out.
Yeah. There's two.
Does it have a weird butterfly on the cover?
Yes, that's it. That's it.
Okay, that's the
one. Yeah, that's the one. And something like that kind of happened to me. Like I wasn't trying to learn about quantum mechanics. I was thinking about brains. I was like thinking really hard for a long time about meaning and neurons and like language, right? And I had what I thought as at the time as like a breakthrough. I was like, wow, this is so cool. And it gave rise to these ideas of kind of like oscillating patterns, like structures that changed, but then repeated and like came back on themselves. And strangely enough, like a few days after that, I had really strong intuitions about physics and quantum physics. And that just sounds crazy, right? It sounds like really weird that something like that would happen. But I didn't care at all about quantum physics before that. Like, never was interested in it. I like read some letters by Einstein, like between Einstein and Schrodinger. I thought that was really cool. And like I kind of was vaguely aware of the debate. But that was some time ago that happened to me. And
I'm assuming you had to study the basics in school at some point or something.
Yeah, I mean, I got I think a minor in math, or I did quite a few physics classes. So, you know, like I was always doing technical things. I was always studying math. I went and did a literature PhD, and I did a bunch of math classes, just auditing them because I really wanted to. And then I switched from literature to studying math. So I was always like very, I don't know, my mind was working that way. But that's like a long way of answering your question. It's like a very strange not answer, right? But the intuitions were basically like, here, this is what I was thinking about. All of a sudden I'm interested in quantum physics. I didn't know very much about it. So I just started reading, and then the momentum just very gradually grew and grew and grew and kept growing, until I ran across, at some point, I was like in some deep discussion group of physicists, like all talking about crazy ideas. And actually, yeah, that's not where I heard about the droplets. I heard about the droplets from Wired magazine. But when I came across the droplets, I was like, this is all happening. This is so close to the stuff that I have been thinking about. And
Tell people what the droplets are.
okay, so the droplets. In 2005, two French researchers in Paris were studying coalescence phenomena of droplets into surface. Like, there's different regimes in which it coalesces or doesn't coalesce, right? And they accidentally discovered that if you vibrated the surface of like a fluid bath, then you could have a little droplet actually bounce there. So it's like silicone oil. It was known that droplets can stay on the surfaces for a while, but this was new and interesting because they were pumping energy into the bath by vibrating it, and then the little tiny droplet was just bouncing there forever. And they made a very
Like on an air cushion, like a hovercraft or
exactly the
something.
air cushion never gets thin enough, basically never gets exhausted. So and then it winds up pushing the droplet back up. And in a certain regime, it locks into resonance. So at that point, the fluid bath, and the droplet are in resonance, and like the whole bath comes alive with these standing waves that the droplet is exciting. And they saw the droplet bouncing, and they saw these standing waves. And this was Yves Coudert and Emmanuel Faure. They had like this immediately was like, whoa, it's a particle in a wave. So they started thinking about quantum physics. And John Bush, who's the MIT hydrodynamics professor, who basically like really drives this field forward now, he told me that he thought that was a stroke of genius because a lot of people wouldn't have thought to go in that direction. They would have been like, oh, look at this cool fluid dynamics thing that we discovered. So they immediately started doing these experiments like, well, what can we learn about this? Does it have anything to do with quantum physics? And there's all kinds of experiments you can do, because if you tune the vibration in a certain period, in a certain like regime of acceleration, the droplet destabilizes from just bouncing, and it comes just to the side of the little wave that it made, and the wave pushes it off to the side, so it moves a little bit, and then it hits again, and the same thing happens, and it moves, so it destabilizes into a walker, and it just goes in a straight line. And so the wave's field is still vibrating, but it's pushing the droplet, and you can strobe the wave field at any particular point. And it looks like, if you strobe it at exactly one period, it looks like the wave field isn't oscillating up and down. It looks like it's just moving, right? And then the droplet is just moving, and it looks like the droplet is just surfing on this wave. So it's driven by the gradient, right? So it creates this wave field, and the droplet gets moved by the gradient of the wave field that it generated. And that is that already has some connections to quantum mechanics. But what these two researchers found is like, first thing they did was the double slit experiment, and like these droplets like diffract with themselves, right? Which is like supposedly one of like the outstanding mysteries of quantum physics, is how can you get something diffracting with itself? And
Can you talk about how they set up that experiment?
Yeah, so the way that they set that up is has to do with the fluid regimes, or the system regimes at different fluid depths. So when the droplet is bouncing, the way that it behaves, the way when it's like walking, depends on the wave field, the gradient as I described, and all that. And all of that is a function of actually like the depth of the bath. So if you change the depth of the bath at any point, you actually change the actual system dynamics. And if you make it shallow, in particular, like actually there is no supported bouncing or walking regime at the shallow place. So the droplet winds up bouncing off of these shallow. So what you have to do is you just make a little underwater barrier. It doesn't actually come up above. It's actually under the oil, and it'll just bounce off, right? So then what they did is they made a wall like that with two holes in it, basically like two slits. And then they had the droplets, and the droplets would pass through one of the two slits. And this is one of the first things that I ever saw with the droplets back in like 2014 or 2015.
But there's a bunch of controversy over this, right? Because it's like such a delicately tuned system that one laboratory could show diffraction, and then other laboratories tried to reproduce it, and then they like couldn't get the exact same outcomes. Is that an accurate representation?
Yeah, I think so. I think the diffraction result is, in a way, like the least compelling one, actually, right? It's the one they started with because that's the paradigm of, quantum strangeness. And then they got a result which actually I don't think anybody was able to reproduce, right? And then the numbers, the statistics were a little bit low, so you would have liked there to be more observations and things like that.
But the reason that I bring that up is not to be like, oh, well, nobody else could do it, but to say that this appears to be a center point of why people will often ignore these hydrodynamic quantum analogs. And I want to get it on the table early so that somebody who like has this in their mind is like a reason why this isn't appropriately applicable to quantum mechanics has had it dealt with, so they're not just thinking of it the entire time. Because in the book, I think you make a really good point, which is that like it's not a perfect reproduction of the system. And
it would be really weird if it was. Like that would be, yeah. We wouldn't expect that to happen in a two-dimensional fluid bath.
Yeah. But yet the insight that this offers you, which is that there is something material and explicable that happens underneath the mathematics of quantum mechanics, is not disproved by the fact that you can't reproduce this deeply parameter dependent experiment of diffraction through double slits.
Yeah, I mean, no, it's actually the opposite, because if you care about this question in the first place, and if you have classical quote unquote intuitions where you think there should be an explanation for the statistics, then the whole body of research is incredibly encouraging, right? So even the fact that you could get a classical system to be like to exhibit single particle diffraction is like awesome, right? Because that's back in the 30s and 40s, everyone was saying it was totally impossible, like, and that there was absolutely no way to ever do it, and it was just a contradiction in terms, right?
And the crazy conclusion that pops out of that, I was hoping we could talk about the positivists for a second, because there's definitely a popular school of thought that's really prominent today in a number of different places, but one of them being quantum mechanics, is that your mind just can't comprehend it. Like humans just aren't up to the task. There's certain things about nature that are just beyond our puny intellectual ability, and I've always recoiled at that kind of anti-human, just, I don't know, it's just so disempowering. And so I'd actually never, I've had people refer me to the positivists before, but I loved the way that you broke this all down, going back to, was it Comte?
Comte,
in the book?
yeah,
Comte, okay. Yeah.
Pronounce it however, yeah. Auguste,
can you tell people about that a little bit? It's a crazy lineage of this oscillation between, I don't know what you want to call it, realism and unrealism.
There's a part in the book that I don't think made it in. There's a lot of things that didn't make it in. But in that I was talking about that particular thing that you just raised, which is very prominent in modern physics. So prominent, in fact, that I think it's probably the standard view. The standard view, this has nothing to do with the issues we're discussing or like the quantum anything. It's a much more general thing, which is like you were saying, like humans have very limited meat computers. So like if something makes sense to us, it's probably wrong, right? Like it's not deep enough, right? Why should God's thoughts make sense to human beings, right?
And you hear this from your teachers, by the way. Like I heard that from my teachers in physics since the beginning, pretty much. Like, and I would read all of these pop sci books I get out of the library when I was a kid, the Michio Kaku and Brian Greene, and they're all repeating this mantra, and it was just so heartbreaking. And I deeply had an intuition that couldn't be the case, but it was just really sad to just hear it from everybody. It literally dissuaded me from going into physics for another decade or so because of,
I fully agree with you, right? I think it's wrong personally. But you also can see where it came from. Because basically originally where it came from is the death of mechanics, right? Like where we had like classical mechanics where you had forces, you drew force diagrams, everything made sense. You like have pressure on stuff, right? And the thing is like, okay, well, what's a force, right? So they start like in the process of doing physics, they discover the electromagnetic field, right? Now they have the electromagnetic field, and they're like, okay. And then they tried to come up with mechanical models of the electromagnetic field, and they couldn't do it. Like basically nothing worked. And there was a period of like 50 something years, 70 years or something, where they're trying to come up with mechanical models for the luminiferous ether, and they just can't do it. And then instead, what happened is like, actually what we need to do is explain mechanics with electrodynamics. So they switched the order. So now actually electrodynamics is really what's creating all the forces, right? We don't understand it, but actually maybe that's because there isn't a mechanical model at all, right? So then right around the time that all of this stuff is like, all this stuff is in the air and it's oscillating around, 1905 comes along, Einstein says there is no ether, special theory of relativity, and then it's like never looked back since then. So
and is it your perspective that the philosophers picked up on this from the physics community?
So going back to positivism now, we can change, like we can go back. But that I just wanted to throw out there because that's something that didn't wind up in the book. But I think that that's how all of this started, basically, where it's like we can't understand it, and if we could understand it, then it must be wrong. So the thing about positivism is a little bit different. It's actually more of a priori commitment than what I just described, I think, right? And the thing, like Comte's whole thing was essentially to do away with speculation into essences and causes, which he saw as actually just a transitional period between total primitive thinking about gods, and the will of like immortals being behind everything, and real knowledge. And he characterized real knowledge as just like a mathematical theory of stuff you could observe, basically, right? And he called that positive knowledge, right? So everything else is, if you're thinking religiously, then you just see like the will of God and everything, and that explains nothing. And if you think scientifically, then you don't think about why something happened. You only care about how it happened, and the rules of sequence, the mathematical rules of sequence that explain what will happen next, right? So Newton's theory of gravity is a good example. No one knew what gravity was, didn't need to know. Like you can explain the planets and the moons and the tides and all of this with it. And then
the critical delineation there is that they can describe the patterns of the motions of the planets and so forth, but they don't actually explain the cause.
Exactly. That's the critical delineation. And what he said is like, forget about causes. That's philosophy. That's like you started with religion, then you go to philosophy and you're like, what's the cause? And he's like, shut up. Learn to describe phenomena. Forget about causes. You'll never know, right? He's like, it's beyond our mind. And this is the connection between positivism and what we were just discussing. Yeah.
But this is really weird too, because he's got some like really culty aspects to this, right? Like this is a guy who on paper is like, okay, so you go from this theological, infused with God worldview, then you go to the world of like Aristotelian essences and these attempts to put material spirits into object, and then you go to like real true absolute rationalism, and then he's also like recruiting for cults where there's churches all around the world. Like I don't understand how those two things relate.
This is one of the craziest things I learned researching this book. I couldn't believe it. Actually, he found it.
As I read this section, I could just tell that you were like, what the fuck?
Exactly. What the fuck? This is another one of those things where I was like trying to make the book shorter, and I was like, I gotta find things to cut. And I was like, I am not cutting this. There's no way. Oh my God. So you can kind of understand where he's coming from, because his view became roughly that in the future, the term positivism or positivist will become generally known. and it'll be basically now like I have founded like the next stage of human evolution or whatever. And not only that, it will be associated with like everything good, like everything positive in humanity and so forth, right? So he did become I forget the actual quote of someone who was studying him, but he said something like, in the place of the dispassionate scientist, he became more of like a priest in his like zeal and the ambition of his aims, right? So that definitely happened, and that was so strange. And he basically, I mean, it's hard to even talk about because it's so weird. Like he basically made a new calendar for humanity where all the months were based on the names of great men like Goethe, Shakespeare, right, Gutenberg, whatever. And then he characterized the function of the brain, like every single possible function of the brain. He wrote it down, and then he made like a whole secular like secular right, basically, of like this is now how we should be organizing society. um and he asked the French government to give him the Panthéon, like the Pantheon, and like at like the top by the big garden there, which is just like, that's just madness, like give me the like one of the most important buildings in the country and I'm gonna spruce it up with my religion. So yeah, it's so strange. But the thing is, it actually caught on. Like that's the thing is he definitely touched on something because it was, I think, a big bull market in rationalism, and around this time is when like they were like scoring hits over and over and over with science. It's like they predicted the return of Halley's comet like within a few days, right around this time, and like so many new things were happening. And this is also like pre-Nietzsche, right? This is like also like the kind of ferment in Europe that Nietzsche came out of, where he was like criticizing religion and that kind of thing. So I think that that's part of maybe like turning their back to religion, or like embracing science um, as a real competitor to explaining the world, had something to do with that. Obviously, it went way too far.
Okay,
Uh,
so tie this back to what you said, didn't make it into the book, which was the switch between mechanics leading, or bodies interacting leading to forces, versus the forces being the driver of everything after the development of field theory. Like,
yeah,
is Comte, how much later is Comte? Is he trying to piece together what happened in the ashes of
he's
starting
before
with
this.
math first?
This is why there's not such a direct connection.
I see.
He was actually well before this. He was like in the 1820s, right? So this is before even light was considered to be a wave, right? Like
When
this
when was Faraday? 1860s?
Faraday was, no, I don't think he was the 18. No, no, no. 18, so Maxwell, 18 Max was like 1850s, right? So Faraday's are the early 1800s, right? And like maybe even late 1700s, right? So like the heat equation is in the early 1800s. They still don't know what heat is. Um, Arago and Fresnel are like early 1800s, 1818, 1820, 1830, right? Then Maxwell is like 1850s, 1860s. So the theory of electrodynamics didn't come out until like the middle of the 19th century. Okay, so all of these issues weren't even there. They didn't even arise. Like these issues, and I mean like the stuff on like electrodynamics and like what the paradox that Einstein resolved, right?
And when is Comte in
But
all of this? I'm sorry.
the
Comte is
company,
like 1820, right? So like he's like early.
Mm.
Yeah.
but he's kind of picking up on some general zeitgeist about this reaction to deities controlling everything and so forth.
Well, this is what I'm trying to get at, right? Because if he's contemporaneous with Faraday and he's paying attention to what the scientists are doing, then he's watching Faraday wrestle with trying to come up with a material explanation for electricity and magnetism and kind of fail. No?
That was later.
I see.
So yeah, I mean, I don't know exactly how much he knew about electrodynamics. I don't think that he discussed it very much. Most of all the stuff of Comte that I read, he didn't discuss electrodynamics at all. And mostly he was talking about Newton, Fourier, right? And these kinds of people. So and he had to bring it back and connect it to those two things we've been talking about. There isn't actually, I mean, I think he probably would have been happy with Einstein because, Einstein's move in 1905 where he got rid of the ether was considered a positivistic move. And he even said, Einstein later when he's talking to Heisenberg talked about it. He said, yeah, it was. I nevertheless still wrong. Like, because Einstein repudiated that later. He was like, you can't do that. But I think the connection is that it's kind of like a fortuitous one. It's like basically Comte came to these conclusions about the limitations of human knowledge just independently. And on the basis of that, kind of tried to accelerate the progress of science.
Well, they sort of feed back upon one another too in the modern discourse. I don't know if you've kept much of a pulse on the analytic idealism realm of things, but it's very similar to this proposition that you can never really know what's going on because everything's kind of happening inside of your head.
What is? I don't even know what analytic idealism is.
Well, one sec, but I'll like to get to that. But these movements often refer back to quantum physics in the modern era to justify their conclusions. Like
a lot of things do that.
Analytic idealism, from what I understand, is essentially the idea that the universe is the only things you can say about the universe on first principles is that you're experiencing it. And therefore, the unreality of any of these quantum mechanical experiments and so forth is because of the fact that it's just happening inside of your head anyways. Is that fair? Nasty says it's not fair.
I think an analytic idealist would
All right,
blow
help
a
me
gasket.
steel man them better.
Blow a gasket.
Yeah, like I think I can hear them screaming already in the background.
Yeah, Shiloh's an idiot. Tell me how it is.
I think that it is a consciousness first universe. It is that the field of consciousness is the fundamental, and everything is this wave function of consciousness. Like, there's no material reality. Everything is one unified bath of silicon oil. And we are all just these vibrating manifestations. And so interactions are real insofar as there's consequences of the interactions. But there is one substance, and that substance is consciousness. And from it springs everything.
And I feel like you hear things like, the double slit experiment works that way because it's your perception, it's the observer that's making it happen, something like that.
I think that the analytic idealists do use quantum mechanics to make this claim, but I think that it's often less explicit than that and more kind of pointing to, well, quantum mechanics makes a probabilistic and statistical interpretation of the world, and they tell us that that's the only thing that's down there, ergo it cannot be made of matter, it has to be made of something, space-time is doomed, behind it lies consciousness.
Yeah, see, like your mind is it's just all in your mind.
It's not your mind, it's the consciousness substance that you are a vibration of. Like, that's the thing, is like, for them, that's a significant delineation, and I think that we've been really pissing off the analytic idealists lately, and so I'm trying to represent them as fairly as I possibly can.
Okay, so fine. So they reify this idea of consciousness into a substance and it's vibrating, and that's the cause of everything.
Yeah.
Okay.
Yeah. And so the reason that like stuff is weird in quantum is like, well, why wouldn't it be weird? It's all statistical mechanics anyway.
Isn't there a flavor of this positivistic, it's beyond your limits kind of thing?
To varying degrees. I mean, like, in the sense of the Kantian, the thing versus the thought of the thing. I think that there is the sense that, like, we can never know the thing, in itself. We can just know the experience of the thing. And so I'm like, you can tie this back to the larger question though. Now that we've punched down
Well,
on
it seems to
analytic
me,
ideas.
yeah, I mean, jeez,
I
we've had a
mean-
couple of these guys on the show before, and as soon as we start talking about physics, it all goes to hell usually.
Right.
But I think the wider point here is just when I look back across the history of rational discourse, and I can go all the way back to the Greeks who are getting, various guys are getting busted up and thrown in prison for different acts where they're essentially, there's these two forces, right? I love the word forces. There's two forces at play in history. And one of them is like, hey, you can understand how stuff works. And one of them is like, hey, other people can tell you how things work. And that's because they're in communication with some divine
Right.
source of knowledge. And it just seems like the latest iteration of this variety, where it's like, go study second order differential equations and then you'll understand how gravity works or something. And then you go, I'm a naive idiot, so I go and do that. And I'm just like, wait a second, this isn't actually explaining anything. This is just describing with greater detail how these things unfold. And so it's all a little bit of a scam, but I feel like there's been these two forces at odds with each other since ever. I just feel like this is the latest incarnation of that.
Well, in some ways, it's a synthesis, right? Because the thesis is you can understand everything. The antithesis is that only some people can understand everything. And the synthesis of that appears to be, well, there's not really anything to understand. I'm like, okay, we've made progress.
Oh my God. That's the synthesis of every Hegelian dialectic, basically. Just throw it in the garbage. Boom.
Done. We've solved it. Wash our hands, go home.
Well, dude, another part of your book that I've just been referencing nonstop since I read about it was how you discuss the age-old practice of people trying to throw other people, of public-facing media trying to throw dissenters under the bus, right?
Anonymously.
Sometimes anonymously, right? I remember, I think it was a London Times piece where this guy's just talking trash about Thomas Young.
Edinburgh Review.
Edinburgh Review. Yeah.
Because he dare go against the great Newton, right?
Exactly.
Because, of course, Young has this wave theory
Yeah.
of light, and Newton has this corpuscular theory. And the scouring remarks from the press were just unbelievable. Like, how dare this? I should actually pull it up. We should find one of these quotes. It's so amazing, though. It's like, how dare you go against the great Newton? You're not even a scientist. You're just a mere physician or whatever the heck he was.
Exactly.
That is an unbelievable series of quotes that you dug up from the past.
Yeah, I read that whole thing. It was gross, man. And I read all of Young's reply, which is very noble and beautiful. But the whole episode is just crazy.
Didn't he have an existential crisis from this? He thought about quitting physics and
no, basically what he kind of, I mean, yes is the short answer. I don't know if I would call it that, but he basically said at the end, he wrote a pamphlet that was the response to Henry Braham. Braham wrote two of these. The first one Young didn't reply to, but the second one he did, and both of them were kind of surprisingly influential. So especially the second one, I think, had an effect on Young's career. He must have, for him to have taken it seriously, or if not his career. He was a doctor, right? So it's not his career, but he was lecturing at the time. He was circulating among the Royal Society and giving talks in the Royal Society and all this. So it definitely affected him. And at the end of the pamphlet, he said, "Hitherto, I shall no longer. I shall restrict myself to only medical, investigations." Right. So basically, he's he basically stopped. He said, "I'm going to stop doing science. I'm going to stop investigating anything." Right. Which is just incredibly sad. It didn't work out that way, right? He just kept going, but it did have an effect, and he started publishing anonymously more, and he didn't ever really fully develop his wave theory, right? That actually that Fresnel did.
Which is crazy because he's got to be one of the biggest intellectual titans of all time.
Thomas Young?
Yeah.
He would be so cool to hang out with. That guy was like, yeah, like there's so many people wrote such complimentary things about him, you know, like from
he was doing music stuff. He was doing all these ancient language translations. He was doing elastic mechanics. Like the guy was just insatiable.
Wasn't he instrumental in translating the Rosetta Stone?
Yeah, if you read these books about that, then then basically he's one of the main guys that shows up. So there's like a competition across the channel, like in France and England, to translate the Rosetta Stone. And then I don't really know the names other than Young, but one of them, basically I think both of them succeeded, more or less. And Thomas Young was instrumental. Yeah, he like had read the Bible twice by the age of like 7 or something like that. It was just like mental. Yeah.
Pardon the interruption. I have to ask you for a favor. If you like what we do on the podcast and you appreciate the ideas and conversations that we bring into the world, come over to patreon.com/DemystifySci. For 75 cents a week, you can help us keep this ship going. You can help us get to the place where we can record our conversations in person instead of over Zoom, and make sure that we never have to stoop to selling you supplements, tchotchkes, and razors. So see you at patreon.com/DemystifySci.
Cool. I just was looking up Faraday and Comte's dates and stuff. So Faraday did a bunch of his like major experiments in like 1831.
Okay.
And 1830 is when Comte's first book came out.
Interesting. So do you think that there was a back and forth between them at all? Or some kind of...
I think that all of this stuff happening in London.
Hey, tilt your computer down again.
Oop, there you go.
No, a little bit more. I'm sorry, you still have like a full, like, head's worth of headroom. A little bit more. There you go.
Yeah.
Perfect.
No, I think because like he had probably written the book before the first one, before Faraday even proceeded, like even like published. Maybe electromagnetism electrodynamics had been around for like 10 years before. It might come up in the second and the third volumes of his course on positivism, which I didn't read as carefully. But yeah, so far as I know, basically those things are happening at the same time.
I guess I'm trying to figure out the zeitgeist at the time of Comte and Faraday, as well as what happens downstream and how these ideas become culturally fixed, right? Because from my read of Faraday's notebooks, Faraday is trying to figure out electromagnetic radiation from a really mathematical place, because he's a proponent of this like Boscovich point atom, where the atom is this mathematical point in space surrounded by force fields, and bonding is the product of force fields that are harmonious with one another as these different mathematical points come into contact. And so for me, I'm reading this and I'm like, oh, it seems like he's leaning heavily into this idea of an immaterial foundation for everything already. And Davies is also a proponent of this. So his mentor is basically guiding him in some ways in this sense. And then when we get to Maxwell's field equations, people are still trying to kind of put some sort of material frame on it, but that might be the last place before it breaks down completely. Because you said something where it's like, they tried to get a material mediator for like 70 years, and then they threw in the towel.
Mm-hmm.
So, okay, why did they fail? And why did they throw in the towel? Does it have to do with what Comte is proposing earlier in the century, where the popularity of positivism has gotten to be so profound that scientists, after, again, 70 years of attempting to explain this, finally just are like, I guess it's not for us to do.
Right, because we're barking up the wrong tree. And that's actually a solid point, because Mach, who's even better known positivist than Comte, was very influential later on at the turn of the century. And Einstein was very influenced by him. He said that all of physicists of that generation imbibed his ideas like mother's milk, right? Mach's ideas. And when Einstein killed off the ether, it was explicitly a positivistic move. Like he was aware of that. And then he inspired Heisenberg in his whole thing in like 1923, 1924, something like that. To actually, it's probably, yeah, I think it was 1924 or 5, to restrict all theoretical machinery in quantum physics to things that could, in principle, be observed. That was his phrase, right? So, and that was, he's like, well, I'm only going to talk about things that, in principle, I can observe. So everything else, in principle, you can observe, which is already giving the whole game away because you're basically settling the question before you even prosecute the question, right? But then Heisenberg and Einstein talked about it. Heisenberg said, didn't you do this very thing where you got rid of things that, weren't necessarily observable? And then Einstein said, yes, I may have used this line of reasoning, but all the same, it's invalid. So yeah, I think it's a pretty good point. Mach, I don't think he was so directly influenced by Comte. Mach was very much his own thinker, but he did admire Comte. And he said that Comte did a lot to do away with metaphysical superstitions. Yeah. So
Can we go back to the Einstein killing the ether thing? Because I've told this story a number of different ways, and one of the ways I can tell the story of the death of the ether is through the attempts to detect it. So through the
Michelson-Morley experiment,
something along those lines. Yeah. Why do you pin it on Einstein? Do you have any paraphrasings of his own ideas or anything that you can point to?
I don't think that it's a simplification to be like Einstein did it, for sure, right? Because yes, you have this famous null result, and you have a lot of difficulties leading up to that, right? Like stellar aberration, the electrodynamics of moving bodies, like all of this is stuff that they were trying to figure out. Seems strange, and they couldn't piece it together. And when I say that, he killed the ether, kind of what I mean is he explained his special theory of relativity explains, quote unquote, the problems, makes them go away, right? In a kind of like an elegant manner. Like, you only have to accept two axioms, basically, two postulates. One of them is fine, the other one is super weird. But once you accept them, then all of the problems go away. But what it means is like there's no absolute reference frame for space. And like the ether, you can never ever detect it moving, so you might as well just stop even thinking about it. So that's why he's often, I think, associated with this specific capitulation, because the special theory of relativity really was a very significant advance, and it was accepted almost immediately. It laid the basis of his fame. The other two miraculous papers that he wrote in the same year were not as instantly influential. Yeah.
Can you talk about his transition towards the opposite perspective?
Yeah, I think it came about through his long work on general relativity, right? Where in order to establish general relativity, what he realized is that like space itself has physical attributes. It has something in it which bends light and changes the otherwise what you would think of as a straight line through it, right? Changes that into like an ellipsoid or whatever. And so he realized that actually the that's kind of what people were imagining when they thought of the ether, is like some sort of space-filling medium that had physical properties. So he said, actually, it would have been more accurate, rather than to say that there is no ether, that we've kind of like reimagined its properties, right? And now it's called space-time.
He called space-time a non-kinematic ether when he spoke at Leiden.
Yeah, I'm not surprised at all. And there's a book on this that I haven't fully read. I've just like read little excerpts from it, and it describes this kind of this like I don't know, like transition or arc in his thinking.
Because by the time we get to the Bohr-Einstein debates, he's squarely of the opinion that there must be a physical explanation for what's happening, even if he can't articulate it. And I really loved this section of the book, by the way, because you cobble together these like news reports and these subtle observations of how everyone's behaving at the conferences, right? At these gatherings where, you know, the headline is like, you know, Bohr trounced Einstein in this debate because he can't explain the, you know, the wave particle duality or whatever. But the subtext is that Bohr and Heisenberg are visibly upset that they can't recruit Einstein to their side. And so it's a little bit of a Pyrrhic victory because nobody seems to really have this victory at the end.
Yeah, I think that's right. And I think that what Einstein was trying to do is he was trying to show that the uncertainty principle and quantum mechanics in general were inconsistent, right? That they were like somehow fundamentally wrong, like they had to be thrown out. And that's what he was unable to do, right? So Bohr would save the day after careful analysis every time, and everyone would be like, okay, it's all good, right? We're fine. And that is, you know, if you can't do that, if you can't like, you know, slay quantum theory, that doesn't mean you're wrong, right? His whole deeper point is that it's incomplete. That there's more to the story. And he eventually gave up trying to do that. He did admit ultimately that the uncertainty principle was consistent and that the whole theory itself was consistent. Yeah. So
where this gets weird, right, is that the uncertainty principle is a statistic, probabilistic view of reality that has been made into reality itself, right?
let's see. I think that that's basically correct. Yes. So Bohm said something like this. He basically said they have a method of computing and they want to identify their method of computing with reality. And in the Festschrift that was put together for Einstein towards the end of his life, was collected in this book called Albert Einstein, Philosopher Scientist. Like tons of people wrote papers for this, and then he replied to them at the end. And I would suggest anyone to read it. It's just so his writing is just so beautiful, and like at the end of his life, it's like so cogent, right? And makes so much sense, everything. But the main thing he says about the uncertainty principle there is that he basically says that the people who have written all these papers, more or less claiming unanimously or kind of in concert with each other that quantum mechanics is complete, are basing their treatment on the uncertainty principle. And the fundamental problem I have with this approach is its positivistic character. Because that's what you do in positivism, is you're like, look, I've got a mathematical theory that works, job done. Right? Which is ridiculous.
Okay, so something that I think is really applicable to this is in the book you do this extensive treatment of the similarities between the form that the wave equation takes and is it heat?
Yeah, this is like one of the major points in the book. Yeah.
Do you think that you could kind of, in brief, sketch that argument out? Because I think that it is a powerful argument of parallels because I think that if I remember correctly, what you say is you're like, look, we figured out a mechanistic understanding of heat, despite the fact that we had the mathematics that were almost positivist in their character, and figuring out the mechanism actually was valuable and important. And this equation looks just like the quantum equation with a slight modification, ergo it suggests that there too is something there that underlies the statistical mechanics.
Yeah. So this this particular period of the point of the book, or like section of the book, was, I think, probably the hardest one to write, and it was how it was like the result of what I said before, like, how am I going to talk about this? Like, what am I going to say, right? And I didn't know any of this before I started. I basically pieced it together, and none of the points that I make in this whole section are original, but I don't think anyone has made them collectively. And I think that the fundamental point is exactly what Einstein was saying, but people don't appreciate that. They actually have forgotten the context and the history, and so they don't. When Einstein talks about quantum mechanics being incomplete, like statistical mechanics or something, people like don't get what the point is, right? But Bohm, von Neumann, Yammer, all of them, these people who were like in it at the time or very aware of the history, they make similar points. And when I give talks about the book, this is what I talk about essentially, because it's like kind of like the fundamental thing for me. Might just be psychological, but whatever. So yeah, I'll spell it out real quick. There are uncanny parallels between the history of thermodynamics and the history of quantum mechanics. So uncanny that everyone should know about them, in my opinion. Okay, so there's multiple things that characterize the theory of heat in the 1800s, and a lot of them we've kind of touched on already. And this is why we touched on them, because this is why they're in the book. First, no one knew what heat was. Okay, so Fourier in early 1800s, and then again in like 1822 or something like that, came up with the heat equation, which is a differential equation that we still use today to explain the evolution of heat in materials. Okay, the thing is, nobody knew what heat was, so they had a differential equation that worked, and Fourier wrote hundreds and hundreds of pages, like pure like mathematical deductions based on this equation, right? And people still teach it today. But the thing is, like, they had these theories of heat. There were two. One is that heat was an actual like chemical element, like hydrogen and oxygen. It was actually like a material thing. It was invisible. It permeated other material things. It weighed nothing, maybe very, very little. And the particles self-propelled, which is why heat spreads out over time, right? But they also interact with other forms of matter, and they attract sometimes other forms of matter. And there's things you can do to release these heat particles and so forth. The other that was called the theory of caloric, calor in Latin being heat. So then the other theory was vibrational, which several other people believed, and the idea is, well, no, heat is a modification of matter. It's a state of matter where, like, if matter is moving, then it becomes hot. Okay, so then we've spoken quite a bit about Comte. This is where he comes in, because Comte has a very, very strong opinion about this, and his opinion is that this debate is meaningless, right? Nobody is ever going to figure it out. It's beyond the capacity of our mind, right? And instead, what we should do is just admire Fourier, who wrote down the heat equation, right, and explained heat insofar as it can be explained to us, as like a mathematical rule. Okay. So shortly after Comte died, statistical mechanics started taking form, and it was built up from an old idea by I think it was John Bernoulli, one of the Bernoullis, who basically had speculated that it's called the kinetic theory of gases, that gases are made of lots of little tiny particles that are moving around all the time, and he was able to deduce like basic properties of gases, like their temperature and pressure and things like that, from that idea. So people started thinking more and more about that. And in particular, Boltzmann and Maxwell figured out, just by deducing, like mathematically, like let's imagine that atoms are real. Let's imagine they're moving around like billiard balls. There's like lots and lots of them. What would be their statistical distribution and their speeds and things like that? They were able to actually explain heat on that basis. So basically, they did a whole bunch of statistics and came up with what's called the Maxwell-Boltzmann distribution, which is like a probability distribution that determines the heat of a gas. But it's actually not about heat; it's about velocities, right, of particles. And on the basis of that, all of a sudden, we're thinking about heat as being the statistical emergent property of like an innumerable number of collisions. Now we start thinking about collisions and how statistical properties evolve in time on the basis of underlying collisions. And now we can start talking about the diffusion of lots of stuff, like particles in water, prices, like up and down through time. And it turns out that the heat equation is actually a diffusion equation, right? It's actually an equation that describes how things diffuse through time in certain conditions. Okay, so that's like the history of thermodynamics. Quantum physics is like almost identical. It's crazy. So like, first of all, we have a differential equation. We don't know why it works. All we know is that it works. The differential equation, Schrodinger's equation, differs from the heat equation by a constant factor of like I. It's like a complex number, right? It changes everything. It changes the equation like fundamentally. Taking any differential equation and changing even a sign will change the whole thing. So it's not like, oh, it's the same equation. It's not at all. But the connection between the heat equation or statistical mechanics and quantum mechanics is not new. It's not something I discovered. Like other people have remarked on this, right? So that's one thing. Second thing, just like in thermodynamics, there were multiple theories about like what's actually going on, right? So we have, I don't know how many, like 24 different quantum interpretations, right? Don't have to mention them. There's just like tons of different ones. Also, positivism has like followed quantum mechanics around from the beginning, just like the heat equation, where people were saying, there's nothing underneath this. Don't even examine it. Why are you going to waste your time, right? And it became like actually like culturally anathema, career suicide to do something like in that direction. And then finally, quantum mechanics is like the wave equation is statistical. It's describing a statistical distribution, right? So you have all of these connections between thermodynamics and quantum mechanics. The only thing that isn't like fully slotted into place is that in thermodynamics, they discovered the underlying causes, even though someone told them they were never going to do that, right? And in quantum mechanics, no one's done that. So the question is, well, is it possible? Well, if you kind of buy into this argument of parallels, as you called it, you should believe that it's going to happen eventually.
Do people, though,
Buy into the argument?
believe that it's going to happen? Yeah.
Most people don't. Most people aren't even aware of the debate, I don't think. They think it's been sorted out. They think the debate's over.
It's actually crazy. So we talk to a lot of people that focus on consciousness and, like Shiloh said, analytic idealism, all sorts of philosophies of this. And oftentimes they'll have sort of heterodox ideas about where consciousness comes from and what it is. But universally, they start from the most consensus basic principles of quantum mechanics. And they're like, well, people have won Nobel Prizes for this, ergo it must be accurate. And there's no reason to re-examine the assumptions that underlie the mathematics, or like the assumptions that tell us what we should do now that we have the mathematics. And it's always really stunning to me because it feels like such a huge barrier to overcome now that prizes have been given. And for the last 100 years, we've spent basically our time and effort on this self-congratulatory parade of having discovered that the universe is inexplicable and unreal at its most basic foundations. And I'm like, this is something that Shiloh and I always are preoccupied with, of how do you go back on that? How do you switch directions?
It is like seemingly insurmountable, right? To the point that you basically are discounted pretty much right away if you even just go down this road, right? Like the gatekeepers are like the serious academics, the ones that control the journals that people read, like won't even give you the time of day. But that's not there is reason for hope, right? And the reason is that this is not unusual. This is not weird. Like, actually, this happens over and over and over again in human history, in the history of science. And this is the main reason that all of these parables in the book, where basically talking about superseded scientific theories that we look back on now as being obviously wrong, but in their time were considered to be obviously correct. There's so many examples of that. And we were talking about Henry Brougham and his attack on Thomas Young, right? Like the light particle duality, the particle wave duality in light is a really good example of this, because it goes back and forth multiple times, right? Where like Newton sets the stage, everyone just kind of agrees with Newton because he's Newton. So everyone believes that light's a particle. And then Young has the audacity to disagree, right? And disagree with everyone, pretty much everyone, right? And he gets attacked for it. Fresnel also agrees with him and actually proves that it is a wave. There's a back and forth for like, several years until into like, I think 1930 or something like that. Finally, everyone realizes it's a wave. Newton was wrong. We were all wrong. You were all wrong, whatever. Light's a wave. And it goes on being a wave until an unknown patent clerk says, no, it's a particle in 1905. And no one believes him, right? And he basically argues for something like 20 years that light's a particle. And then eventually everyone's like, wait, like the Compton effect, all of these things that you can't explain except thinking that light has corpuscular nature, all of a sudden now it's both. So that's only one example, and it's a kind of not the best example, because that's still an outstanding mystery, right? But thermodynamics is a good one. Like, I described the theory of caloric and vibration. It wasn't like they were on equal footing. Everyone believed in the caloric theory. Like, if you read the Encyclopedia Britannica from like the 1800s, it talks about how heat is generally agreed to be a form of matter, right? The theory of miasma is another good one. Like, this whole theory of how diseases spread was just totally wrong, like fundamentally wrong-headed, but everybody had that same idea. All of the health ministers, like dealing with like outbreaks of cholera in London, all of the scientists, all of the smartest, most educated people, right? And then tectonic plates is another one. Like, nobody believed in the theory of plate tectonics, right? Like, Wegener came along. He wasn't a geologist. His PhD was in something else. He had this idea that was so obvious that like even like a child looking at a globe would have this idea. The continents fit together like puzzle pieces, right? But he was just like mocked and ridiculed. This kind of thing is very common. It's just extremely it's like disturbing living through it and seeing through it at the same time. That's like hard to deal with.
There's this weird thing that people always do, and they do this with the past hijinks of states doing evil things in the past, where they're like, well, that's history for you. Those primitive peoples, they assassinated world leaders and they were wrong about scientific theories, but we wouldn't be like that. This astronomy course I teach at the university, the textbook loves the Copernican revolution story. They have a chapter dedicated to it, but then they can't possibly conceive of anything similar happening at the point that we attribute 96% of the universe to stuff we can't see or measure or anything, right? And it's just such a strange blind spot that we have when we look back in time, where we think of ourselves as the apexes of human knowledge and understanding in this way that it's so bizarre.
I think that's fundamentally what the book is about, because I can't explain the quantum mystery, right? So, it'd be nice if I could, but it's a popular science book. So it's like fundamentally about the debate. And then I try to actually comment more deeply on the debate and point in the direction that we should be looking in my opinion. And that's how the book ends. I don't know if you got to the ending, but that's it makes me, what you just said makes me want to read the last paragraph of the book, because that is exactly what I'm saying in the last paragraph of the book.
Do it. Yeah. Do you have it nearby?
Yeah, I grabbed it. I got the
Yeah, go for it.
All right, here we go. I mean, it's basically exactly what you were saying. Here we go.
These things bear repeating.
Sure. One popular textbook on quantum theory has this for the final sentence. Quote, "It is entirely possible that future generations will look back from the vantage point of a more sophisticated theory and wonder how we could have been so gullible." Unquote. As residents of the breaking crest of time, we have the feeling that we are wise. We are not wise. We are just like the fools who believed that phlogiston, caloric, and miasma were real. We are no different than those who looked up at comets and proclaimed them to be windy exhalations. We poured the foundations of geology and biology so recently that the concrete is still drying. We think we are modern, but we are not. We are the ancients. When future generations look back at us, what spectacle will we make of ourselves? What feasts will we be for their historians? It seems certain that our century-long assumption that quantum mechanics was a complete theory will be, to them, lunacy on a civilizational scale. Our descendants will shake their heads at us. They will look at themselves and say, "We know better now, we moderns. They were foolish. We are wise."
I love that.
Yeah, it's beautiful. But everybody's got to go get this book. I really mean it this time. At people, go and get this book. This was one that I just loved reading. I read it over the course of a couple of weeks, as I would have a little bit of time before I was teaching. When I had to drive an hour to this other town. Anyways, I had a little bit of time, and I really didn't want to put it down each time. It was just so fascinating, the human side, and I keep saying, the actual experiences in the words of the people that were living through all of this just makes it so real in the modern sense. You can see the same dramas playing out today that have been playing out time and time and time again. This pendulum swinging between these different stasis points of understanding, and then defending those stasis points, and then they crumble, and it's just so predictable.
I wonder so I read basically all the way through the first 200 pages. I started it last night, and I read until I fell asleep. And I was just like, it's good. It's when there's a book that's it carries you along. And at first I was reading the introduction, and you mentioned something of in chapter 50, and I'm like, who the hell writes 50 chapters? And then as I got into it, I realized that they're each they're very short.
Yeah, some of them are a couple pages, yeah.
And the shortness of them allows you to make a single point without any excess. And by the time that you get to the end of the chapter, you're like, okay, now we have to go here. And it's just, there's something about that structure of it that, despite the fact that it's a long book and it's technical, it just pulls you through each point. And I can tell, as I was reading the stuff about heat, I could tell that you were wrestling with figuring out how to make sense of the story for the person who came along. And it was just very masterfully done. And something that I didn't get to was how pilot wave theory is involved in all of this. And I don't know much about pilot wave theory, and so maybe you could basically lay that out and then connect it to the hydrodynamic quantum analogs as well.
Definitely. Yeah. So this is one of those really important kind of historical things that people who care about this should know about. Most people don't know about pilot wave theory. And essentially the way that it went down is that we talked a little bit about Einstein, and the quantum theory was kind of developing in fits and starts from like Planck in 1900, all the way up, for 20, 30 years. And this French physicist named Louis de Broglie was involved in that, right? So shortly after World War I, he started working in his brother's lab and working on getting his PhD finally. And he considered this point that Einstein was arguing over and over, that light is a particle, which was kind of freaking people out. Like, a lot of people were very against it, Bohr being kind of probably the main one. And de Broglie basically said in his PhD thesis, like, maybe it's both and everything is both. Maybe an electron is actually not just a particle, maybe it's also a wave. So this is the wave matter hypothesis. And it was tested very, like, shortly after he proposed it, and it was right. So he made what most historians recognize as one of the most fundamental contributions to all of the development of quantum theory. He did that on the back of, like, very concrete images in his own mind of essentially like a corpuscle, like a particle that was oscillating and phase locked with a ambient wave. So the phase locking was super interesting because when the corpuscle moves, relativity says that things should contract and slow down. And he was able to connect the relativistic change of the wave as the wave is moving. The oscillation of the wave actually slows down and it maintains its phase locking with the particle. So this is like not some kind of vague idea, right? It was like a very concrete proposal for how you could get particles and waves together. How could they be the same thing? And he developed over the course of a few years this theory called the double solution, which is roughly what I just described. You have an oscillating particle, it is phase locked with an ambient wave, and the particle itself moves in reaction to the wave that it's phase locked with. So his idea was, well, we can get non-Newtonian movement out of these particles if they're interacting with this wave, because what happens is, like, we can get, for example, diffraction, right? We can get single particle diffraction because if you have a wave and a particle, the particle goes through one of these slits, but the wave goes through both of them, and then the particle will interact with the wave that came through the other slit, and then it'll change its trajectory. So that's how he thought of these things. He thought of them as, like, actually very concrete physical pictures. And that is the origin of pilot wave theory. So,
and you make this connection to the hydrodynamic oils on droplets because the waves that are paired to the particles also have this state memory. There's like hysteresis to the way that they move, and they're informed by everything else that's happening in the bath. And so it's this very physical model of the pilot wave theory. Is that the principle?
So when you write down the math of the bouncing droplet system, you wind up basically doing pilot wave theory. And just think about what I just said. You have a particle that's oscillating in de Broglie's model. You have a droplet that's bouncing up and down in the hydrodynamic case. It's phase locked. The particle's phase locked with the ambient wave. And in this case, it's in resonance with it. So it's basically the same. And then the particle moves based on in de Broglie's theory, it's based on the gradient of the phase of the wave. And in HQA, the droplet moves based on the gradient of the wave field. So it's gradient-driven motion. You basically have pilot wave theory again. The thing that de Broglie didn't have at all was memory. And that's something that's kind of quite cool and new about the HQA system. It's like pointing in a kind of interesting direction. It's like maybe we need to think about integral differential equations more deeply, and like the hysteresis, as you were calling it. So yeah, that's pretty cool. But the connection is extremely close. It's like basically pilot wave theory, right? Like it got rediscovered in a lab completely separately, like in 2005, like totally independently. So it's pretty cool.
How does de Broglie's theory not have memory? Like all oscillating substances should have some hysteresis, right?
No, I don't think so. So um, the let's see. I guess we'd have to like try to pin it down, like what you mean by that, because
Okay.
you might be right in this particular sense, but like the way that, for example, the wave equation works is not that at all in 3 dimensions. It's like um, you only ever experience the influence of a single point in time at a specific time. Like you're not like going back through all of time to get to sum up your influence, right? Like I can explain it a little more, maybe better in a second, but I want to understand what you mean first.
Okay. Well, if I was to think about, if I was to use the hydrodynamic analogy to think about like particles and waves, the wave has to be in some kind of substance. And so
Sure.
when you talk about there being memory inside of these chambers, what I understood is that the waves that are produced by the particle when it starts walking will like interact with the waves that are bouncing around inside the chamber to produce a new kind of standing pattern.
Yeah, because they're standing waves, right? So they like once they get laid down, they don't last forever. They decay, but they do. They're not like typical waves. Like if a typical wave is like a raindrop hitting a puddle, it just spreads outwards, right? So these standing waves are different than that. They basically go like this, and they stay there, and then they slowly fade away, right? But they're kind of like everywhere.
But the particle is moving, and so
The
it's
particle
happening.
moves, and then it goes and it winds up interacting with its own wake, as it were, or its own history. Yeah.
Exactly. And so that's memory in this system, right?
Yeah, because what you can imagine, like, I don't know, 10, 20, 30, however many distinct points that the droplet hit, those are all the centers of wave fields that are vibrating at varying amplitudes. You add all of those up, and then that becomes the specific wave field now that the particle interacts with.
Okay. And so if the wave, de Broglie's pilot wave theory is talking about a wave and some kind of etheric substance, then it should be interacting with itself over time as the particle moves, the same way that it does in the hydrodynamic analogy. As
I
long as it's a substance that
Yeah,
has some kind of ability to where it's exactly the same thing. The particle creates this disturbance that is the wave, and then it moves, and then that disturbance is still radiating outward from the previous position.
yeah. I don't think that's what he imagined, though. I think this is where this is the crucial distinction.
Mm.
I think that he imagined not that the wave field was necessarily centered, like there were multiple centers of this wave field through time, just like a single center of the wave field now.
Mm.
And potentially what you have is that wave field then maybe has like bounced off from an obstacle and is coming back or something like that, right? I don't think that it was ever very well developed. Like it's like coupled nonlinear differential equations before computers existed. So
Mm.
like it's not that much that he could do with it. Um, Maybe von Neumann could have driven it further, but it's hard, like very hard. And so I think that's the distinction between de Broglie's system and the HQA system, right? Was like
Mm.
he imagined that the ambient wave field always had just one center, which is where the particle was.
But as the particle moves, the do you get what I'm trying to say? Like, I guess maybe a different way of asking this is, do you know if he imagined the wave as being in a wave of something, or was he still in this paradigm of pure statistical mechanics that it's an ideal wave that the minute that the particle moves, the old one vanishes and there's no there's no interaction between the previous state and the next state. Do you get what I'm trying to get at?
I think so. Like the pure probability interpretation wasn't around at that time. That came like right around the same time he was thinking all this stuff up. I mean, he published his PhD thesis in 1924. Schrodinger read it, took it with him, and came up with the Schrodinger equation on the basis of his PhD thesis. Okay. And then shortly after that, Schrodinger's equation was interpreted as giving a probability of something happening by Born. So de Broglie wasn't thinking strictly in terms of probabilities, and he always criticized that, right? He's like, well, not always. Like he eventually, for like 20 years, he actually just towed the party line, as it were, and taught his students the accepted quantum mechanics. But his later writings after 1952, 1953, he you can tell he's like talking about this. Well, we have a pure probability, but supposedly it's different than other typical, probabilities. So at least he targets it, like he kind of singles it out as something that is maybe a little bit strange. Yeah. I think we got a little. I don't know if I was answering your question. I feel like I went off on a tangent there, but
No, I think so. I mean, I think that you're suggesting that he didn't really work out the dynamics of it. And the dynamics are always the tricky thing, right? Because if you can describe something that's stable and then you have to solve a really gnarly equation in order to be able to talk about what happens to it at like T1 versus just T0, and then T2, T3, T4, you run into a much gnarlier problem.
he was able to do some of that. Like if you look at the 1927 the famous Solvay conference like proceedings, his talk actually had dynamics in there where he was saying this is the trajectory of the particle. It goes like this, and then it like if it's going to bounce off of something, it goes like this, and then it goes like this, and then it bounces off, right? So it was like this micro structure of something going on that is like this really interesting like wave pattern, and that's what they were discussing, right? So it wasn't like quite as like empty as maybe I kind of made it seem. There were actual proper deductions and predictions that came out from it, and that's what Pauli criticized, and so on.
I think that I understand what you're saying. You're basically saying that with the hydrodynamic analogy, the wave and the bouncing droplet move together, but in de Broglie's theory, the pilot wave is generated and then the particle follows the undulations of the wave as it travels.
Yeah, so in the HQA version, the particle creates the wave and then it moves on, the wave stays there, bound, like kind of vibrating, right? And you have a whole bunch of these waves, and they sum up. And in de Broglie's theory, you have the particle and it's the center of a wave field, and they move together.
Got it. Okay, I think that makes sense. Where are you going to?
I mean, what's cool about either case is that you start to get the picture that the medium has a state of motion that's informing the particular area, like the particle. And so and that gels with me, because when I think of what a particle is, it's really a measurement or a predicted measurement. And so that your instantaneous measurement would reflect the dynamics of the whole system interacting makes a ton of sense. It also explains why you wouldn't be able to detect the ether, because the ether is going to stem from the matter itself. And so you're not going to be able to find this soup that's doing something different than the quote-unquote particles themselves. Nasi looks super disturbed.
No, I think you're right. My immediate question was, okay, well, is there a test that can be done to determine whether or not there is a medium with memory? Because it seems like the analogy is really appealing because it makes sense that if there is some kind of substance that I don't necessarily think fills the space between atoms, but is like the extension of the atoms that is able to hold some kind of state memory. From that, you get these resonant patterns that emerge inside of stable systems. Like some of the way the droplet experiments that you showed recapitulate the orbital diagrams, which is really interesting, right? You have these seemingly chaotic systems that enter into pockets of resonance that look like the s orbitals, they look like the p orbitals, they look like the higher degrees of the hydrogen wave function. And so if the analogy continues, then that seems like that's reflecting a substance that is waving also in reality. And the question then becomes, is there a way to detect it? Or do we just have to accept the axiom that it must be there and we have to think of it? Does that make sense?
Well, I mean, nobody took a picture of molecules vibrating to deduce that heat had to be the vibration of molecules.
Yeah, that's where my mind was going too, is like the thing that's so condemning about positivism and is basically like the death blow to the whole thing, if people would just notice, is that without believing in atoms and then developing the whole theory of knowledge based on that, atoms would never have been observed. Right? So like we can now take pictures of them, we can move them across substrates with like scanning tunneling microscopes. We can make movies, like stop action movies with atoms, right? But if Comte had gotten his way, it would have basically closed the door on progress until someone finally decided, to hell with it, like let's actually imagine that atoms might be real, and what can we deduce on that basis. So, you know,
So this leads us really neatly into another question that I have, which is that at the center of quantum mechanics is this idea that the uncertainty principle is not an artifact of measurement, is not an artifact of just how difficult these systems are to probe with the tools that we have available. It's that it is literally a fundamental principle of nature.
Yeah.
And I'm like, I've tried this analogy out before. It's like the throwing a rock at a football, where it's if you're trying to take a picture of a football and you're doing it with a camera that throws rocks, you can probably only figure out position or momentum each time that you throw the rock because you destroy the trajectory of the football when it meets the rock. And so when we're doing experiments that look to see whether or not the uncertainty principle is accurate, what we're doing is we're doing the detector equivalent of throwing a rock at a football. And so we destroy the system. But the same way that you can take a radar image of a hurricane with light and actually see the system without destroying it, it's because the wavelength that you're using to probe it is at a different scale than the system itself. Does that make sense?
Mm-hmm. So that, I think, was pretty standard. The pretty standard interpretation of the uncertainty principle for a long time. And this is, I think, one of the main things that Bohr was saying for a long time, which is basically what you were saying. Like we can't ever escape this need to disturb the system. And because we can't ever escape the need to disturb the system, all of these profound things kind of like follow on from it. But it's interesting because he stopped talking like that after the EPR paper, because the EPR paper basically showed that you should be able to violate the uncertainty principle with entangled particles going off, and you just measure one of them. And now you should be able to deduce with probability unity the state of the other one, even though you didn't disturb it at all. So I don't really have I don't have a pat answer about this. I feel like I don't fully understand the uncertainty principle and how it actually interacts with things and what the right way of thinking about it is. But my own current thinking of it is consonant with what I generally try to do, which is to connect things to like the broader context, right? Like if you know that there's something that's very, very trustworthy that you don't want to get rid of in the broader context, which actually is relevant to what you're thinking about, then that can help you find your way. And this is one of the reasons why I like think about history so much and think like kind of general things. But the thing about the uncertainty principle is that it's not like unique to quantum physics, right? It's actually a feature of Fourier analysis. Like it's a feature of putting things together with lots and lots of wave modes. And there's a part, I think you didn't get to it yet, Nastya, but there's a part in the book where I talk about how the uncertainty principle also applies to audio sampling, which it does, right? And Bohr, in his like famous Como lecture in 1926 or 27, that was his fundamental point about when he finally discovered complementarity, right? He used telescopes as an example. It had nothing to do with quantum physics. It was like this very well-known trade-off in actually telescope design, where you have like a certain basically uncertainty principle between two quantities, right? Where they can't ever, like the product of the uncertainty of both can't ever be smaller than a certain number. So I think that, in my own opinion, I think that's probably the right way of thinking about it, right?
Can you break down the audio sampling thing for people?
Okay, so the basically you've got two things. You have the you have like the position of a wave train coming in, and then you have the frequency of the sound. Okay, so if you have total understanding of the frequency of the sound, like you know with total certainty what the tone is, middle C, whatever it is, right? What that corresponds to is a sine wave of a very specific wavelength going off forever in both directions, right? Which means that its position is totally, completely undefined because it goes off to infinity in both directions, okay? Similarly, if you take a whole bunch of different frequencies and add them together, you can get the actual sound disturbance to bunch about a specific point. So you add more and more and more and more and more and more, frequencies until you get like your chirp actually just happens at a moment in time. So you know exactly where the sound disturbance is, right? Then you have so many modes, you don't know what the frequency is anymore. Like you basically have infinite uncertainty in the frequency, right? So that's the uncertainty principle. It works for audio. Like it's basically Fourier analysis. And there's like the discrete. I think the place that I first noticed this was the discrete Fourier transform, which is maybe like the most used computer algorithm in the world. It's just very, very useful for all different sorts of things. And the discrete Fourier transform has an uncertainty principle in it. And
Can you just tell people what that is really quickly? I mean, we've probably all heard of it before, but is it fair? Can I just summarize it as like the ability to deconvolve a complex waveform into its constituent frequencies? Is that a reasonable?
Yeah, I wouldn't say convolve, but yeah, basically what you do is you have two different like domains. You have like a time domain or a space domain, and then like a frequency domain. And the two of them go back and forth, where like you can represent your thing in one domain or the other domain. So you in Fourier analysis, you just have wave modes, like I was just describing, and they're continuous. And you have an infinite number of possible frequencies, and you can add them together. You can add an infinite number of them together, and then you create a subsequent waveform which has a specific shape. And you can create, this is what
So you
Fourier...
can like make an orchestra out of a bunch of pure tones, basically, or backwards, I suppose.
In fact, that's the only way you can make an orchestra, is out of a bunch of pure tones. Yeah.
And like for like the audio nerds, all of us musicians out there, this is basically how equalization works, right? You get this, if you see like a parametric equalizer, you get bins of all these different frequencies that your music is representing at any given instant, which are necessarily inferred because they're instantaneous. And it's basically just this simple Fourier transform. I don't know if it's simple or not, but it's pretty simple calculus.
There's a whole bunch of functions that are defined on this space once you set it up. And the discrete Fourier transform is like the easiest way to understand it, because you can do all of the math with like a finite number of modes. Like you don't need an infinite number of frequencies, right? And then like you do have convolution, and you do have like modulation, and all of these functions that you can define on your mathematical object. And they wind up, when you're thinking in terms of audio, they wind up having specific effects like band pass limiting, right? You just cut off, cut off all these frequencies, or like shifting
harmonic distortion,
all this stuff. Yeah, all of it is basically just functions that are defined on this particular mathematical domain.
I'm gonna have to think about this some more. I think that there's something really deep here, but I don't have it yet.
Yeah, I'm kind of there as well. You mean in terms of refining the problem of the uncertainty problem?
Or refining it as being some fundamental feature of a specific type of analysis, where there's like limitations to what kind of information can be contained at any given moment. So that's interesting.
Yeah, there's another part in the book where I talk about exactly this, and it's kind of amusing, but I don't even know where it went. But yeah, you probably know the one I'm talking about, where I talk about the guy who says that on the basis of very deep insights into audio sampling, he's discovered a philosophy that also applies to political science and rockets and right, and then he basically says like all of this profound stuff, right, about the world on the basis of this very like constrained area, right? And like no one would take that seriously, but it's disturbingly close to the way that Bohr actually argued.
I'm gonna have to go back to that section.
I can see if I can find it. Hold on. Talk about.
You know the one I'm talking about? Maybe you do.
I didn't make it there yet.
All right. Well, I can try to find it then. This is the one where I kind of criticize Bohr pretty strongly.
How dare you?
I know. Cool. So basically, it's the end of the chapter, and it starts with this quote by Mara Beller, who is outstanding. And she says, "Complementarity is not a rigorous guide to the heart of the quantum mystery, nor do Bohr's numerous analogies between quantum physics and other domains, such as psychology or biology, withstand close scrutiny. Complementarity does not reveal pre-existing similarities, it generates them." So that's the quote. And then I have two paragraphs following that. I say, "This is what happens when an entire worldview is built up from Fourier analysis. What a surprise that an algorithm used to compress cat photos for transfer across the internet actually means that, as Heisenberg put it in his uncertainty paper, quantum mechanics establishes the definitive failure of causality, and that we must renounce the idea of atoms actually existing independently in the external world. Skepticism is warranted. Fourier analysis is just a mathematical tool, like proof by induction, appropriate in a variety of situations. What we should conclude from its applicability to quantum theory is not obvious at all. Saying that Fourier analysis works because it grasps the essence of any situation is quite the leap. Because the uncertainty trade-off applies when sampling audio, should we make profound conclusions about the nature of sound itself? We could do this, but why? Such philosophizing is unnecessary and highly fallible. Imagine a musician philosopher who does this, claiming that insights gained from sampling audio have redefined the very concept of music. Then he goes further, insisting that this new understanding has profound implications for visual art, politics, and rocketry. Imagine he says these ideas would provide religious comfort and be taught to children in the future. It's possible he could get many followers if he were charismatic enough and understood the guru game, but only among the credulous. Literate and critical people would consider him sadly misguided or clownish, or perhaps a cynical fraud. Yet, as we have seen, this is uncomfortably close to the way Bohr actually argued."
Oh man, so you do touch on something here which is extremely important that we can't close this conversation without mentioning, which is the re-enchantment of reality that quantum mechanics offers people. And it, I don't think that the popularity of these mystical interpretations is a result entirely of gatekeeping. Although, like you said, a lot of these more physical interpretations aren't welcome in the standard literature. But I don't think it's just that. I think it's that people really like the idea that the universe has mysteries up its sleeve that we'll never get to.
I
Like
agree.
there's something that it unlocks inside of people that welcomes a way of thinking that has been with us since we first rubbed two sticks together around a fire or something. Like this need to experience. Look, I'm going to back that up and say I think we're all very aware that there are magical things in reality. Like, what the hell is love? What is heroism? What is courage? What is like there's all these elements of reality that we experience and we're familiar with that we want somebody to tell us are a legitimate part of the universe. And so when the physicists are like, well, there's all this crazy, wacky stuff happening you can't understand, maybe that's where all of the magic can live all of a sudden. Maybe it somehow emboldens us to entertain the idea that there's something beyond these mere atoms grinding into each other. Because we're all deeply aware that there is. I mean, we're a bunch of atoms sitting here talking over Zoom. That's freaking nuts. And so we all recognize that something very strange, I'm just using the word magical to express how miraculous it is that a bunch of atoms decided to get together on a Sunday afternoon and have a conversation about the nature of reality. Like, that's super weird and profound. And I think that people expect the physicists to give it back to them. And I just feel like there's a huge metaphysical weight, especially in the dwindling popularity of religious thought in the 21st century in the West, where we need that. We need that reenchantment. And people look to the physicists and they're happy to deliver it.
Yeah. I two of my best friends told me that the entire point of my book, that I was like my thesis, whatever, it was depressing, super depressing, right? Yeah. For that reason, right? It's like, I think that there is I don't know if it's a type of person or a type of thinking, which feels like Dawkins wrote a whole book about this. Like, when you unweave the rainbow, you've taken the magic out of it, right? And now, oh, it's just it's merely light reflecting off of raindrops, right? And it's just a bunch of mere atoms grinding into each other. This is, I think, maybe like the movement of mind, where you're like, all of a sudden things seem much more depressing, right? Um, and I just don't. I mean, I definitely see that, and I think it's a real thing. But I don't believe it at all. Um, and and neither did Dawkins, and neither did Feynman. Like, Feynman uh, did a bunch of visual art, like a bunch of paintings, and some of his like inspiration was this idea that actually there's so much beauty in scientific truth, right? And it's not like you're not taking anything away. I wish that I'd read Dawkins' book on weaving the rainbow, because then I probably could just like repeat the things that he said there, because I think he's generally pretty good with this kind of stuff. But
I
that's
see
my
it as just a separation of abstraction layers. It's like you can definitely look out on a physical landscape and you can see a bunch of, ants marching along. You can see a bunch of humans crowding into a stadium or doing some physical action. And like, everything's physically consistent. You can come up with force laws to describe their interactions and collisions and everything. But that's never going to get you to the heart of understanding the fact that there's these two teams that people embrace and they're having this mythical playoff that's in some sense harmonic with the total experience of being a human being on Earth and competing with other individuals, and it's this giant, like multi-layer removed abstract play of this fundamental experience that we're all having in our conscious realities. And there's just, I almost want to simplify it and say the physicists should stay in their lane and stick to physics and like leave the rest of stuff to the artists and the athletes and the poets. And, there is a lot of magic left in the universe. I just don't know I don't know why we expect physicists to be the ones to hand it to us on a platter. That's where things go off the rails for me. I mean, physics is the king of the intellectual castle for some reason that I can't totally comprehend. Like, we could have easily looked up at the stars and been like, hey, those stars aren't moving the way we thought they were. Maybe they're alive or something like that. Like, that wouldn't be an irrational thing to suggest if the biologists were in charge of the castle or something. But instead, the physicists are like, no, it's dark matter, or something, right? And it's just, it seems like a very arbitrary distinction. I can imagine a planet, 1,000 light years away where the biologists were in charge of astronomy instead. Or, the physicists didn't make any claims about the cosmos or, cosmological claims. Like, they didn't really talk about our human relationship to reality in any way or really even talk about reality. They just talked about physical processes unfolding. Like, that would make a lot of sense to me.
I think this is the first time I've disagreed with you.
Let's do it.
I don't agree with that. I agree that you can imagine it, and I agree that it would be fun to imagine, right? Like, you could like write cool stories about that. But I think there are real, genuine reasons that physics is in the place that it is, and that people wind up looking to physics as some sort of authority more than biology, as it were, right? And it's not that hard to search. It's just the fact that physics is universal. Like, it's so the methods of physics do work for stars, and they also work for chemistry. And not only that, yeah, I know.
To a point,
everything's to a point, but it's like you can't apply the concepts of biology to stars. Like, if you try that, you wouldn't understand stars. And
but the stars don't move the way they're supposed to. I mean, that's for sure. Like the galactic rotation problem or something, right?
Yeah.
It's like,
but the other thing I was going to say is, like, if like physics also talks about small stuff, right? Like, really, really, really small. Like, there's no boundary to its like scale. It talks about all the smallest stuff and the biggest stuff, everything. And in particular, if you talk about the small stuff that everything else is made out of, then you have some sort of claim to like fundamental understanding, right?
Fundamental physical understanding for sure. But I mean, you're not going to find the love particle between me and my wife or something, right? Like, there's certain phenomena that require different levels of abstraction in order to grok.
Yeah. So,
but you also can't imagine love occurring at a particle level. Like, we sometimes use that language to say that
it's a big part of the universe, though, right?
It is a big part of the universe, but so this, I think, relates to what we were talking about yesterday. Remember when I was like, hey, I think I've figured out why analytic idealism doesn't make any goddamn sense, to kick the idealists again, where we have this vision of emergence as being something big that comes out of many small things interacting and producing a novel phenomenon. But we never have a system where a really big thing suddenly like interacts with itself to produce the smaller things that make it. Like, that doesn't make sense. Like, that's not the arrow of time. That's not necessarily the direction of evolution. By the time that it gets to the smaller things, it's dissipated, it's collapsed, the emergence no longer is there. So you can't have emergence if you're going down. You can only have it as you're building smaller things up into the big thing. And so if you're trying to understand something like love, which is at a much higher abstraction level than the atoms that are involved in it, you still are left with the question of like, okay, well, what is the arrangement of atoms that produces love? And so even if the stars are alive, you're still stuck with this material question of like, okay, well, how are the atoms inside of them interacting to produce the aliveness that we can detect. And so it seems to be the grounds from which everything else springs. It's the like Cartesian tree.
Look, all I'm saying is that even if we all sit down today and nail a material model for the actions of the medium that results in all of the equations that we love and hate from quantum mechanics, even if we have that, we still should probably leave love to the poets and the musicians and the novelists and literally anybody else. Like there's pieces of the universe that are important that physics just isn't the right toolkit for.
Yeah. That I completely agree with. I think the only thing I was pushing back on is you basically saying, why are physicists given this like special role? We could have given that to anybody. That I think is the wrong thing. But I totally agree with you that like I don't think anyone is going to argue that there's like you can find the differential equation. Imagine there was a theory of everything and it was one differential equation. Oh, now we understand love. Like, no, it's not it. That's not at all what physics is trying to do anyway.
Mm.
So I guess that's the point, is there are important parts of the universe that aren't really questions for physics, but I think we expect physicists to have answers to everything. And that's where things get a little off the rails.
So I think that there might have been something that happened with biology declaring itself to be a materialist discipline that meant that like spiritual instinct had to go somewhere, and for whatever reason physicists were more permissive to it. Because I think that if you've ever seen a creature that goes from being alive to being dead, it is impossible to not just spiral on the fact that it is the exact same stuff in roughly the same conformation as it was moments ago, and now it is no longer. And there is something insane that has happened that science has absolutely like no word for, and biology very firmly was like, there's no such thing as a soul, it's just atoms. And so we're like, okay, well clearly there's something. And so if people are like, well, reality cannot be understood and it's weird and mystical and biology is quantum, then perhaps it's these like quantum superpositions that are maintained which create the illusion of soul. And we're kind of happy to put it there because it's like, we don't go there anyways.
Yeah. There's the mysticism that has kind of coagulated in physics is definitely a very interesting cultural phenomenon that has happened. And there's more things that didn't make it into the book that are interesting in this context that I was like thinking of that I kind of wanted to talk about. And one of them, well, first of all, there's this book, How the Hippies Saved Physics, which is all about the counterculture and like a bunch of kind of fringe physicists in the 60s working on Bell's theorem and the strangeness of quantum physics as directly kind of directly tied into counterculture and like the free love movement and like, you know, altered states of consciousness and all this kind of stuff. So the Dancing Woolly Masters and the Tao of Physics, both of these books came out of people from that group. And those two books set the tone for physics in like the popular imagination. And it's still like reverberating, right? So there's definitely that part, like those things, like that's like straight up mysticism, basically, right? And they were attracted to that, and they were working on it, and they were trying to understand how the quantum, you know, world, what it was saying about like deep aspects of reality and stuff. The other thing that I think is cool and interesting is that the whole like Copenhagen kind of orthodoxy, very like, and it wasn't just Copenhagen, it was like also the von Neumann Wagner interpretation, which was like your mind, consciousness collapses the wave function, right? That is just like candy, for like, the mystical worldview, right? All of these things, they just like were a perfect recipe for like the profligation of mystical concepts um, and I don't know exactly the causal directions, and I don't think that I can very fruitfully speculate on like the instincts of mind that led people to this, or if like spiritualism needed to go somewhere or whatever. But the thing that seems at least historically accurate to me is that it was like a favor, right? It was perfect. It was a perfect setup for the people who thought in this way, and they used it like quite a lot, to the point that, you guys know about the Sokal hoax. This is pretty cool.
No, do you?
Oh, you guys will like the Sokal hoax. I'm pretty sure you guys will like this. So this was like the late 80s or like maybe the 90s. I'm forgetting now. But this guy named Alan Sokal wrote a paper um, called something like On a Hermeneutical Investigation of Quantum Gravity or something like that, right? So he's this physicist. He wrote a paper that he sent into this cultural studies journal called Social Text. And it basically kind of like was just gibberish. It was just a bunch of like like lingo thrown together with some physics words and some cultural studies words, and it was all just like basically nonsense. And they published it, and then a few days later he announced that it was a hoax, and that he was calling attention to the fact that basically this whole area of like humanities is just totally messed up. And
When was this, by the way?
when?
Yeah.
Like I said, I think like the late 80s or the early 90s.
Okay.
It's called the Sokal hoax. Yeah. And and like, they're appropriating scientific discussion. They don't even know what they're talking about, and so on and so forth. Okay. So then this just, as you can imagine, it just completely exploded. And like so many journal articles, newspaper articles were written about it. Derrida wrote something about it. All of these people were just like, for a long time, writing about it, and they still do from time to time. But the reason I bring this up is that Mara Beller, who I already referenced in this conversation, wrote a really great paper. I think it was in Physics Today, called like The Sokal Hoax, At Whom Are We Laughing? Right? And she was a historian of quantum physics. She wrote this book called Quantum Dialogues, which everyone should read who cares about this subject. So in that, she said, okay, yeah, you guys are making fun of these people for accepting this, but Sokal started his paper by citing Bohr and Heisenberg, saying that objective reality has disappeared, and we no longer believe in the classical worldview. And then she goes on over several pages, basically talking about all of these founding fathers of quantum physics, Pauli, Heisenberg, Bohr, who said all this stuff that really is basically like quite mystical, and like, not really consonant with the supposedly hard-headed scientific like approach to things. So she was basically pointing out a kind of hypocrisy there. And I'll stop talking now, because those are the two main points I wanted to make.
That's really cool. I'm going to go read about that since we get off the phone here.
I wonder if we can land on the question of what this does, right? So when we talk to people about this, I think that Shaila and I both have had this experience where you sit down with somebody and you're like, hey, maybe there's something about the way that we're interpreting quantum physics, or something in the way that we're interpreting quantum physics that isn't quite right. Perhaps there is something that's material underneath the statistical mechanics. And a lot of people that are very, very smart, that are very technical, that are very mathematical, engineers, finance people. A lot of the students in our PhD program are kind of like, who cares? It works. Like, we have technologies, we have computers, everything works fine. Like, what's your problem?
That's
Like,
hilarious. Really? People say that? That's absolutely hilarious.
it is the default response.
You could have
Like,
said that in the Stone Age. We have hand axes. Hand axes work great. Look at this. I can totally skin a rhinoceros so well right now. Look at this. Why do I need to go any further?
I mean, that's generally my thought too, because I have this thing about the genetic field where I'm like, okay, so if you go back to turn of the century biology, like Darwin's written The Origin of Species, Mendel's kind of figured out some statistical rules of inheritance, then there's all these biometricians who come by and they're trying to figure out the like larger principles of inheritance and how to mathematically model them. And they're advocating for the fact that this is enough, that we can like go forth and study biology from the principles of assortment and what the next generation will look like based off of understanding the characteristics of the previous generation. And simultaneously, you will also have people that are working in the medical field and the biomedical field that are trying to figure out what's actually inside of cells because they have microscopes that let them look into the cells. And so they see that there's these compartments and there's these things that appear to be functional. And so probably we should figure it out. And so they figure out, chromosomes, or actually there's a guy who collects white blood cells and by collecting pus-filled bandages from a hospital, and he purifies the white blood cells and extracts the phosphate-containing nuclein that he's like, I think this is the stuff of inheritance. And so it's just this like unbelievably gnarly process by which people are just eking out discovery by discovery about the material basis. And I'm like, well, what would have happened if we hadn't had microscopes that let us see into the cell? And we didn't really have like super solid biochemistry. And these mathematicians came by and they were like, well, we have the equations that describe the field of inheritance, and statistically it's very good, and there's nothing below it. Like, do we have molecular medicine? Do we have immunotherapy? Do we have gene therapies? Do we have germ theory? Do we have literally like any of the things that have improved our quality of life over the course of the 150 years that we've had them? Or are we just still stuck in the era of, like miasma and homunculi?
Yeah, I mean, this is basically what we've been discussing this whole time. And there's something in thermodynamics, there's actually a quote in the book somewhere where someone says like Comte's position was consistent. It would have been perfectly consistent to say, we understand heat well enough, we got the heat equation, and just not proceed any further, right? And I think that there's just two things that spring to my mind. First of all, there's lots of different kinds of people in the world, thank God, right? And there's people like us, right, who have conversations like this. And there are people like the people you talk to, probably a lot more common than us, who are like, who cares, right? I'm like, that's not for me. Who cares? Like, it's good enough, right? And thankfully, there are probably it was always like this. There were like the people in the Stone Age who were happy, like hitting things with hand axes. And then there were the people in the Stone Age who were like making microblades and being like, this is better, right? Or like, what's beyond the next hill? And someone's like, why would you go beyond the next hill? We got everything we need here. And they do it anyway, right? So that's good. And I think that especially in times like this, which I would characterize as probably a period of stagnation in physical theory, the outsiders and the people who are curious and the people who refuse to just say it's good enough are the ones who wind up contributing. So that's, I think, one thing. And then the other thing is like, what does this do? Like, we talk about all of this stuff. You can talk to a grad student who doesn't care. I think that discussions like this, like any discussions, are actually incredibly important. They're really, really important. And the reason is that there is really, literally no other way to change your viewpoint that isn't, just like random, right? Than actually having discussions with other people where they're sharing novel ideas or new ways of looking at things. Like, again, it comes back to like there being lots of different types of people, right? And I think that this is another thing that I talk about in the book, is like how important viewpoints are. They're like almost the most important thing in science. Like if you take the right viewpoint, you're going to figure out the problem in like a decade. Like the community will figure it out in like a decade if you take the right viewpoint. If you don't, you'll never figure it out. And like I guess maybe concluding thought on this subject for me is that I remember reading a very compelling New Yorker article, like maybe 10 years ago, about a girl who was born into the Westboro Baptist Church, who's basically like born into a like super intense cult. And everybody around her basically believes this incredibly specific, very localized, distorted version of Christianity, right? And that's what she's born into, and that's what she's raised with, people feeding her, teaching her this. And that's what she grew up believing. And she started talking to people on Twitter and Facebook. And over the course of a year or two of just having conversations with people, she realized that it was all bullshit. And she had to leave her whole family. So that is like, there's this period she described where she hadn't left yet, but she knew she was going to leave. And she knew that her whole family were going to reject her after she left. And she said it was like living with people who were already dead. It was like there was going to be a mourning process. She was going to have to say goodbye to all of them, but it hadn't started yet. And it was as if like she's living with people, her own family. After she leaves, she's going to have to grieve them, and they're all going to be gone from her life. It's just like incredibly compelling. But all of that is what comes out of viewpoints. It's like, that's the key thing. So hopefully someone sees this and they realize that quantum dogma is bullshit.
Yeah.
Awesome. Guys, get this book. Everybody who's listening. It's
Escape from Shadow Physics.
Escape from Shadow
Dun, dun,
Physics.
dun. That's what I do every time I hear the title.
That's a really good title.
It's super fun to talk to you. I mean, in some sense, we are all on the same page about a lot of these issues here in this room. And that almost never happens to Nasti and I. So this is, if this is your first time listening to the podcast, this is not how it usually goes.
It's not usually such a love fest.
No.
I was joking the other day when we had a consciousness guy on, where I was like, the movie Saw, where the serial killer invites people to their house and makes them like solve riddles? I'm like, I think we might be the Saw guy.
Oh no!
Researchers.
I'm like I'm usually sitting there praying somebody doesn't bring up quantum mechanics, in defense. Like I'm just praying they don't bring it to, like, especially these consciousness people or people who don't really understand anything about the experiments that give the equations. I'm just like, please don't do it. Please don't do it. And, sometimes they do. And it usually goes off the rails. So anyways, this has been super fun to not
go straight off the rails. Yeah. That's always good. I really enjoyed this too. It was really nice talking to both of you.
Cool, man. Well,
are you working on another book?
Not at the moment. I kind of want to, but I'm trying to figure it out. Like I had PTSD for a while from this book. It was incredibly difficult. And so I don't know what I'm going to do. I think I might write a book about Bell's theorem, but I also don't necessarily want to just write a book about like another book about physics. I had an idea to write something about Mozart. The death of Mozart, I think, would be kind of interesting to write about. I have lots of ideas, so I don't know. We'll see. Yeah.
Where do you post about stuff so people can follow what you're doing?
Oh, I don't post about stuff.
Okay. No website? Nothing?
I don't even have a website. No, I don't have a social media. I have a social media account, but I mean, I have like 70 followers or something, and I never post there. So
right.
I should get a website. I'll get one eventually. And then, yeah, we'll see. I just haven't got around to it.
Are you on Discord ever? If people want to look you up or anything like that? I don't know. It's okay. You don't have to be contactable. That would also.
I don't think I'm contactable, to be honest. I'll make a website at some point. I just keep putting it off. I've been putting this off for years as well. But there are people who have gotten in touch with me circuitously because it's just like so hard to do. Like, why? I'm not trying to make it hard to do. I just don't have, I'm just not, I don't know. I'm like a caveman. I don't know.
That is totally fine. In fact, that sounds very relaxing, actually. Well, anyways, read the book. All the information's there, anyways. So, I hope that it helps everybody in their own quest to understand how things work on this
That'd be cool. Me too.
strange rock drifting through space.
And then I have to say, everybody should come to our conference in Portugal, June 12th to 16th. We're going to be doing basically what we've done here for quantum mechanics for the Big Bang.
Nice. I would like to come. I will try.
It'd be great if we saw you there.
Yeah, that'd be awesome. Thank you, guys.
Thank you
Adam,
so
thank
much,
you.
Adam.
Bye.
And good luck out there.
Thanks, you too.
Bye, everybody.
Bye, folks.
Bye.